Most developers default to OpenAI or Anthropic. It's the path of least resistance. It works until it doesn't. You're renting intelligence. As your user base scales, your API bill scales linearly. Worse, every single token you send is a data packet leaving your secure perimeter. For enterprise applications or private data, that is a no-starter. Today we stop renting and we start owning. Here is the blueprint for today. We aren't just running a script. We are engineering a system. At the core, we have Llama acting as our inference server. It exposes a REST API on port 11434. On top of that, we have Llama 3, the 8 billion parameter model. And finally, the piece we will build a custom Python interface. This wrapper gives us full control over context windows and generation parameters that pre-built libraries often hide from you. The biggest barrier to local AI is hardware. How do we fit an 8 billion parameter brain onto a standard laptop? The answer is quantization. We are mapping high-precision 16-bit floating point weights down to a 4-bit integers. We are trading a microscopic fraction of accuracy for massive gains in speed and memory efficiency. This compression is the only reason we can run this on consumer hardware today. But let's talk physics. You cannot cheat memory requirements. An 8 billion model requires roughly 6 GB of VRAM to run smoothly. If you have a dedicated GPU or an Apple Silicon Mac with unified memory, you're golden. If you are a CPU-only machine, Ollama will offload layers to your system RAM. But be warned, your generation speed will drop from conversational to glacial. You should know your constraints before you build. Let's look at the interface. We will communicate with Llama 3 using standard HTTP POST requests. We will not use any proprietary SDKs, just raw data. We construct a JSON payload containing the model name and our prompt. Crucially, pay attention to the stream parameter. LLMs generate text token by token. If we set this to false, the user waits for the entire thought process. If we set it to true, then the application feels alive. We will implement both of those. You don't just want an answer. You want the right kind of answer. This is controlled by entropy, specifically the temperature parameter. A low temperature like 0.1 makes the model deterministic and focused, perfect for code generation or data extraction. A high temperature like, for example, 0.8 induces creativity but increases the risk of hallucinations. For our utility agent today, we are hard coding this to 0 to ensure reliability. Finally, we need to solve for latency. We aren't waiting for the full HTTP response code. We are opening a persistent connection where the server pushes chunks of data the millisecond they are computed. Our Python client must act as a generator, yielding these chunks instantly to the UI. This is the difference between a tool that feels broken and one that feels like magic. Now it's time to get hands-on. But before we start writing Python code, we need to ensure the engine is idling. If you haven't already, please install Ollama. I'll leave a link in the description. We need to pull the model weights to our local machine. We are using Llama 3 for this density to performance ratio. Let's run Ollama pull Llama 3. Once the model has been downloaded, we need to create a new folder. Let's call it local inference. And let's also move into it. We also create a new Python virtual environment. And after it has been created, we just activate it. Now we install our only dependency, the requests. We are building this role to understand the HTTP protocol, so we don't need heavy frameworks like LangChain. Now let's create a file called localbrain.py. We start with our imports. We need requests to handle the HTTP transport and JSON to parse the neural network's response. We will encapsulate our logic in a class called localLLM. This isn't just neatness, it allows us to maintain state later. In the constructor, we define the model and the host. By default, Ollama listens on localhost port 11434. We also define the specific API endpoint, /API/generate. I also like to include a quick connection check in the init method. We try to hit the host URL. If the server is down, we want to know immediately, not when we send the first prompt. Now, let's build the standard generation method. This is for when you want a complete answer in one go. We define generate taking a prompt. Inside, we construct the payload. This dictionary maps directly to the API parameters we discussed in the theory section. We pass the model name and the prompt. Crucially, set stream to false here. We also explicitly set the temperature to 0. This forces the model to choose the most probable next token, eliminating randomness and ideal for factual queries. We also send a post request. The API returns a JSON object and we don't want the metadata. We just want the text, which is stored in the response key. If the request fails, we catch the exception and return the error. And now this is the most important part. Waiting for a full response feels like a whack. We need to process tokens as they arrive. Let's define the chat stream function. The payload is identical, except we flip the stream switch to true. In the request, we must also set stream equals true in the Python post call. This prevents requests from buffering the entire body. We iterate over response.iterLines. Each line represents a chunk of data sent by the server. These come in as bytes. We decode them to UTF-8 and then parse them as JSON. We check if the done flag is false. If it is, we yield the response text. Notice we use yield and not return. This turns our method into a Python generator, allowing the frontend to consume it in real time. Let's wire it up. In the standard if name equals main block, we initialize our local LLM. Let's test it with a technical question. The question is, explain the difference between TCP and UDP protocols. We then print the prompt to the console, and we loop through our chat.stream generator. Pay close attention to this print statement. We pass end equals empty string. This prevents new lines after every character, and most importantly, we set flush equals true. Python's standard output is buffered. If you don't flush the buffer, you won't see the text streaming. It will just dump everything at the end, defeating the purpose. Let's now see it in action. Let's open our terminal and type python localbrain.py and wait for the code to execute. The prompt gets printed to the console, and now you can see how the output was streamed. We didn't wait for the full response to come at once, but instead we received the output word by word. And there it is. This is real-time local inference. No credit card, no cloud, just pure code. We have successfully cut the code. You now have a private, free inference engine running on your machine, fully controllable via Python. You aren't paying per token and your data never leaves this machine. If you enjoyed this video, please leave a like and subscribe. I will see you in the next one.